Hey, this is Ms. Roberts at Shasta High School, and we're going to be looking at homework help for Core Connections Integrated 1, Chapter 8. First problem we're going to look at is problem number 7 in this chapter. It says solve for each of the following inequalities for the given variable. Represent your solution on a number line. So I'm going to start by doing A, and if you look at it, let's go ahead and distribute this 2 to both the 3p and to the 1. So I'm going to go ahead and write down 6 times p plus 2. And instead of writing the inequality, I'm going to write equals, because our strategy is to figure out where the boundary location is. Where's the spot that divides those points that work with those points that do not work? So I'm going to write 6p plus 2 is equal to -4. I'm going to take away 2 from both sides. That gives me 6 times p equals -6, and I'm going to divide both sides by 6. So we have that p is -1. Again, it's nice to visually just kind of verify that, yeah, I did indeed subtract 2 from both sides, and I can look at that and check my work. And then from here, yes, I did indeed divide both sides by +6. That's why I have that p is -1. Now, this value p is -1 is our boundary location. So on a number line, here's 0, and over here is -1 and -2, for example. Over here I've got 1, and then I've got 2. Well, my boundary is at 1, and I'm going to put an open circle there. And the reason why I'm using an open circle is because my inequality was strictly greater than. So if I see inequalities with the greater than, that looks like a number 7, a greater than or a less than symbol, then we're going to use a open boundary. But if I see greater than or equal to or less than or equal to, in those cases we'll use a closed boundary. The difference is that the closed dot indicates that that point is part of the solution, whereas the open one indicates that these points are that point is the boundary point is not part of the solution. Okay, so now that I know where my boundary condition is, I'm just going to check points above or below. So the point I'm going to look at is this point right here, which is 0, and I'm just going to plug that into the original inequality. So if you look at it, it's going to become 2. Oops, that doesn't look very visible. It's going to become 2, and then times 3 times 0 plus 1, and then on the other side we're going to have the is greater than -4. So in my parentheses, this is equal to 0. So this becomes just simply 2 times 1, or 2, is greater than -4. And that is true. So because this is true, 0 is my solution. And in fact, because that's the side where it works out that it was true, every other point on that side is going to be a solution. So how we show this is then we would shade that direction. So if I grabbed a highlighter, I could grab this color and I could just go shading this direction. So every point this direction is a solution. Of course, the -1 is not included in that solution, because if I put it in, it would be equal to it, and this it has to be strictly greater than. And just to show you what happens if we try to point on the other side, right? If I was to take and put, for example, the point -2 into this, just check out what happens. When I put in -2, it would give me 2, open parentheses, 3 times, and then this would be a -2, and then plus 1. 3 times -2 is -6. And -6 plus 1 would be -5. So this is 2 times -5, which is -10. So this says -10 is greater than -4. This is not true, right? -10 is much smaller than -4. So all the points to the left of this boundary point will not satisfy the inequality. All the points to the right of the boundary point will. So of course, I'm just going to leave parts B and C for you to do now that you understand exactly what's happening with the boundary conditions. And what it means to present your solution on a number line. Identify the mathematical sentence below that are always true, sometimes true, or never true. So if we look at these, some of them are, I mean, obviously pretty obvious, right? This first one, for example, A, it says -4 is less than or equal to 9. Yeah, it's always going to be the case that -4 is smaller than 9. 9 is larger in value. So that's definitely always true. B, it says x is less than 1. Well, that depends on what x is, right? That's a statement that's sometimes true. I can select values of x where that's false. For example, I could say 9 is less than 1. That's a value of x where it's false. This is never true. I could say, for example, -3 is less than 1. That's true. So it really depends on the value of x that I pick. I could pick x as 1. I could say 1 is less than 1, and that's false, right? 1 is not smaller than itself. So for this one with the variable here, that's sometimes true. And in fact, this one right D, that's sometimes true also, right? 3x plus 5 is equal to 2. Yeah, there's a value of x that makes that true. Most values of x will not make it true, but it's still sometimes true that 3x plus 5 is equal to 2, but it's not always true. A statement that is never true, -5 is larger than -2. That's never true. If I was to look at a number line and just consider, here's 0, here's -1, -2, -3, -4, -5. -5 is always going to be smaller because it's to the left of -2. In general, like when we're looking at a number line, those things that are to the left are smaller than the values that are off to the right. So anyways, I think you could probably finish up the rest of those. So in the textbook, there is a part A and a part B for question 9. It says solve each system of equations below. I'm just going to do the one system here. And when I look at this system, to me, this is a perfect candidate for substitution because x plus 10 is exactly equal to y. So that's what I'm going to do. I'm going to go ahead and rewrite the top equation, 2x plus, but instead of writing y, I'm going to use this substituted value for y, right? X plus 10, and that equals -7 times y. Here I go again. This is y, so instead of writing a y, I'm going to open parentheses, and I'm going to enter x plus 10. So there we go. So now if I look at this, the only variable that I have is the x. I can simplify the left-hand side by combining like terms. This is going to become 3x plus 10. Over on the right-hand side, I'm going to go ahead and distribute that 7 to each of the terms inside of parentheses. So that will become a -7x and then plus, well, let's just go ahead and write it. Instead of plus -70, it's just going to be minus the number 70. So let's add 7 x's to each side of that equation. If I add 7 x's to the left-hand side, that becomes 10 times x plus 10. And over on the right-hand side, if I add 7x, that'll cancel out the -7x and just leave me with -70. And then I'm going to take away 10 from both sides. So this is going to be 10 times x equals -80. And then finally, I'm going to divide both sides by 10. When I do that, I'm going to get that x is the number -8. So here's part of my solution. I know what x is, but I don't know what y is. However, the second equation rather is very nice. It lets me write down, oh, y, that's going to equal whatever x is plus 10. So y should equal +2. So if I write my solution down, I believe my solution is, and I'll write it right up here, it's going to be x is -8 and y is 2. Now, I could be totally right. I could be completely wrong. The only way that I'll be satisfied with the correctness of my solution is to go ahead and plug in my values of x and y into both equations and make sure it makes them true. So in the case of the first equation, it says, hey, take 2 of your x's. So I'm going to say 2 times -8, and then add your y. I'm going to add 2, and that should be the same thing as -7 times your value of y. So if I do that, this is going to become -16 plus 2. -16 plus 2 is indeed -14. And over on the right-hand side, -7 times 2 is -14. So, sunshine, hello. That definitely makes both the left and the right-hand side the same. So that solution, x is -8 and y is 2, works for the first equation. And as far as the second equation, I'm pretty sure it works because that's how I got what y was. But let's plug it in anyways. Y 2 should be the same as x, which is negative 8 and then plus 10. And if I combine the negative 8 and 10, I do get 2. So this does indeed give me that 2 is the same thing as 2. So the solution, negative 8, 2, definitely checks. It's the solution to this system of equations. And have fun doing part B. Write the equation of an exponential function that passes through two given points, and you can see there I've got 2 and 48 and 5 and 750. So if I was to think about this in terms of a multiple representation, I might look at a table of values, and I would have my x values and my y values, 0, 1, 2, 3, 4, and 5. So I don't know the 0th term or the first term, but I do know that term 2 is the number 48. So 2 produces 48, and 5 produces 750. So I'm trying to figure out the exponential curve in the form y equals a times b to the x power. Remember, we're not adding a plus or minus c here. We're keeping our horizontal asymptote the x-axis. So this is the form of the equation that we're looking for. And the technique that we've been looking at in class most often is solving a system of equations where we plug in the x and y values from our 2 points, and we basically use those points to figure out what our parameters are. The parameters that we have that we don't know are, we don't know a, right, which is one of our parameters, and that of course is our 0th term. 0, I think it's got an th term, or our first term, or I mean our starting value, right, before anything happens, before time passes. And the other one is b, our common ratio, or our multiplier. We don't know either one of those parameters, and if we could figure out what those parameters are, then we could write the equation that would hit those two values. So let's go ahead and do this. So we're going to plug in our 2 points. Our first point has a y value of 48, so I'm going to write 48 equals a times b to the x power, where x is 2. And then I'm going to write the second equation, y is 750 equals a times b to the x power, where x is the number 5. So what I'm doing now is I've got to figure out how to solve for this a and the b, right? And the technique that I like the most is getting a alone in both of these. And forever, I've divided both sides by, b squared and b to the 5th in this case. But I like this idea that was presented by students in classes here, a particular student who will go unnamed in this video, who said, hey, let's just multiply both sides by b to the negative 2nd power in the case of the first equation. And in the case of that second equation, you can multiply both sides by b to the negative 5th power. And I like it because they don't look like fractions, although they're equivalent to the fractions, but they don't look like it. So in the first case, if I multiply both sides of this by b to the negative 2nd power, it gives me 48 times b to the negative 2nd power equals just plain old a. And of course, the reason why that's a is because b to the 2nd times b to the negative 2nd is b to the 0 power, which is the number 1. Right? So we can keep saying that over and over again, or we can just get to the place where we recognize, oh, this times this is just b to the 0, which is 1. Same thing happens with the second equation. It becomes quite nicely 750 times b to the negative 5th power also equals a. Now, this is sweet because I know what a is in both of these, right? A is my 0th term, and in terms of this situation, right, a is a. This is value right here. So I'm just going to go ahead and set the two expressions for a equal to each other. So this first equation, right, says, oh, a is 48 times b to the negative 2nd. So I've got 48 b to the negative 2nd. And the other expression is 750 times b to the negative 5th power. Okay, great. Let's get rid of our negative exponents. And I'm going to do that by multiplying both sides of this by b to the 5th power. I like b to the 5th power because it's going to have no b's over on the right-hand side at all, and I only have positive powers of b over on the right hand side. So I'm going to hit both of those with b to the negative fifth. Of course, the simplest one is over on the right hand side. That just becomes 750. When I multiply b to the negative second times b to the fifth, that gives me b to the third. So this is 48b to the third power. Okay, so we're getting close, right? We almost know what our multiplier is. What I'm going to do now is I'm going to divide both sides of this by 48. So I'm just going to write b, whoops, I don't know why my pen became red. I'm going to write b to the third is equal to 750 divided by 48. What I could do next is, of course, okay, I'm going to take the time and go ahead and do this problem fairly thoroughly. So the Battle Creek Bakery makes bread in large batches. Yeast is added to the bread dough to create carbon dioxide gas bubbles in the dough. The tiny gas bubbles give the bread its light texture. They also make the dough increase in volume over time, a process called rising. Below is data collected from 6 batches of dough, and you can see that there's rising time in minutes and the volume of the batch in cubic centimeters. So as time passes, the volume of the batch of dough definitely is getting larger and larger. So first thing says, use your calculator to determine the equation of the least squares regression line and create a scatter plot. So I've already entered the data in this particular calculator, and from it I'm going to go ahead and view the scatter plot. So to view the scatter plot, I'm going to go ahead and press second stat plot, and I can see one of them's already turned on. Let me go to it. It's on. It is a scatter plot, and my data is coming. X's are coming from list 1 and Y's are coming from list 2. This is all perfect. I just want to make sure that I don't have any other equations. Oops, no, I don't want that. I want to make sure I don't have any other equations turned on. I do. I'm going to remove that. So now I'm just going to hit zoom, and it's option number 9, and option number 9 is zoom stat. So this is going to create a nice look for this data collection. There we go. This is a scatter plot, and it says that it says sketch the scatter plot, so I'm going to cheat. I'm just going to drag this and release it onto the screen. That didn't happen. Should happen. Did it happen somewhere? No. Oh well. What I could do is just say, I guess I'm just going to have to copy that. So let me go ahead and just do a quick sketch of what I basically see going on here. I see now as I look at that, obviously this is not looking like a line is a good candidate for this data. Let's go ahead and do a linear regression. So if I hit stats, go over to calc, linear regression is option number 4, and we'll go enter, enter, enter. As soon as I do that, there is the line of best fit, and if I want to display that line of best fit on my data, I can hit y equals, and then I can go grab that equation. I think it's stored in vars. Yep, it's a statistics variable, and it's an EQ, and it's the last regression equation. So I'll grab that thing, and now I'll hit graph again. So there is the line that's fitting this data, but you can see it's really out of sync with the data. This is not great. So if I was to try and put the line of best fit on there, it looks something like this. It does say use your calculator to determine the least square regression line. I did a great job of not writing that down. So let me hit stats, calc again, and go down to 4. And I'll just grab that one more time. So that line of best fit is approximately y is equal to, I'll just write 5.4 times x, and then minus 628.01. I'll just do 0.0. Whoa, get back up here. 0.0. Okay, so that's the line of best fit. Now, the next question, it says, sketch the residual plot and interpret it. So I want to sketch the residual plot for this line of best fit with this data. And it's not the hardest thing to do, but it's a little hard to do. So I'm going to, first of all, I'm going to turn off this particular graph. So y equals, when I hit y equals, I can come in and I can turn off the graph. So to turn on and off graphs, you just go over the equal symbol and you can turn them on or off. So right now this graph will not display. The other thing I'm going to do is in my stat plot, instead of showing list 1 versus list 2, I'm going to show list 1 versus the residuals. So because every single time I run a regression analysis on the TI calculator, not only does it create the line of best fit, the least square regression line, but it also captures all the residuals for those and stores in a list for me in the list button. So to get to that, I'm just hitting second and then stats, which is where list is. And you can see it's number 7, residual. So now I'm going to be looking at list 1 versus the residual. And I'm just going to go ahead and hit zoom 9 again to look at it. And there's my residual plot, right? Not much of a surprise, but I can see there's this starting high, going low, and then coming back up high again. So there is a clear pattern in this residual plot. And because of that, that means that this is probably not, a linear model is not great for this data. So I will go ahead and sketch the residual plot. It should be something like this. So here's 0, and you can see I have a large residual, and then the residuals almost 0, and then I have some negative residuals, and then they come back and positive again. So the interpretation of this that I should write down in my homework, in my notes, is that this pattern indicates that a line is not a good fit for this data. Right, so that's what I would write down. A line is not a good fit for this data. All right, so now it says, since this equation involves increasing growth over time, try fitting an exponential model to your data. What is the equation of the exponential model that fits this data? Well, let's do that. That's fun. So in order to do that, we're going to go to stats. Again, calc, just like if I was going to do the linear regression, but instead of doing linear regression, we're going down to our exponential regression, option 0. So I'm going to hit that, go down, and I'm going to calculate that. And it comes up with this. I like this equation. This is super. It says y is equal to, let's see, my 0th term is 23.8, and then times, I'll use parentheses, times b, which is 1.01 times to the x power. So this is great, right? I can see my multiplier is 1.01. That means this is growing by 1%. Is it 1% each hour, right? If I was to take and subtract 1 from that, it would be 0.01. Yeah, so this is 1% growth per hour. So now let's go ahead and this is exciting. I've got this model. Let's go ahead and go back in our scatter plot. We're going to turn off the residual plot, and I'm going to turn back on list 2 here. So now if I hit second, list 2, I can visit that data, view it again. So I'll hit zoom 9 and oops, let me quit this. I'll hit zoom 9. There's the data again. Looks fabulous. And now I want to add overlay on top of that my this exponential curve that I got. So I'm going to go to y equals. I'll leave that one turned on there. I don't want it right now, but I'm going to come down and I'm going to go to vars again, down to statistics, over to equation, and it's my regression equation. And now that I got that, I'm just going to grab it, hit graph, and I should see, there it is. Look at that. That's phenomenal, right? This is a much better model, and this is really what's happening. So this is the exponential model that fits this data. And just for fun, I could come back over and I can say, hey, let's turn on that linear model again. When I hit that, it's just like, yeah, that was pretty bad. In fact, it's so bad, let's just turn that off and just forget. We'll not even talk about that linear model anymore. All right, so then the last thing, it says, make a residual plot for the exponential model and interpret it. Oh, that sounds like fun. So at this point, I'm feeling kind of tired with this problem. It's been a lot of work and a lot of thinking, but I think we can do this, right? So we're going to come back in into our stat plot. The last Regression I did was my exponential one, right? So my residuals are now the ones that apply to my exponential model. So if I come back in here and instead of doing list 1, I'm going to do the residuals. Remember, it's second list, and there they are at number 7. So I'm now looking at the residuals again. I'm going to turn off this equation. So I don't want to see either one of these equations. I'm just going to look at the residual plot. And if I hit zoom and 9, there it is. Look at that. Totally a different beast. Like if you look at my residual plot before, there's a very clear high, low, high model. Now it's like it's here, it's down, it's up, it's down. So the other thing that's important to notice is that these residuals are much, well, they're much smaller than the residuals before. If we were to look at the residuals before, they're large still, right? Let's not kid ourselves. They're still like, 34 off. This positive. This one's got this data point has a residual that looks like it's about positive 61. They're not trivial, but they're nowhere near as large as they were for the linear model. So again, if we were to sketch this, we might do it. It was below, up, up, then there's a down one, an up one, a down one. So I'm not detecting, the clear pattern that I was before when I had the linear model. This is just kind of, this is more random. And that's what we want to see. We don't want to see that there's an inherent pattern in the residual plot, because this pattern in the residual plot indicates a linear model is a bad fit for this data. So I would say this residual plot indicates that this is probably a fairly good model for the data. It's hitting the points better than the other one was. Anyways, that's a very long explanation for this problem. I wanted to do this one thoroughly with you because we're kind of pivoting, and now we're looking at not just the least square regression lines, but we're also perhaps looking at some exponential models. Okay, the directions for this question are fairly lengthy. You can read those in the book. Basically, the gist of it says for these two sets of figures, we're supposed to decide if these triangles are congruent, and if they are congruent, we're supposed to write an appropriate triangle congruence condition statement, and then we're supposed to figure out what x is using those. So if I take a look at this, this first set of triangles, clearly these sides with 2 tick marks are marked congruent. So I'm going to highlight those in this particular color. And then I'm going to go to, I guess I'll use this green. This angle is congruent to this angle. And then the other thing that's true, and we see this a lot, is they share this side down the middle. So because of that, these two triangles are congruent by side, and then the angle I marked in green, and then side. So by SAS, the triangles are congruent to each other. Now, these two sides here were not in, they don't have tick marks at all, but because these triangles are congruent by side, angle, side, it has to be the case that all pairs of corresponding sides are equal in length. So therefore, this side that's labeled 6 times x plus 6 has to be the same size as this side, the side that's labeled 8x plus 2. So because they have to be congruent to each other, right, I can set these two expressions equal and solve for x. So if I take away, for example, 6 times x from both sides, that gives me 6 equals 2x plus 2. If I take away 2 from both sides, I get 4 is 2x. And if I divide both sides by 2, I get 2 is what x is. So x is 2. Now, I don't believe, it didn't ask me to figure out how big those sides are. It just said find x. So for this particular problem, it is SAS congruence, and the two sides are congruent. Therefore, when I set them equal to each other, x ends up equaling 2. Something fairly similar is going on. I just caution you to think about some of the pieces that you know there. What's x and what are some of the other things, but you should be able to handle that just fine as well. Okay, finally we end with question number 13, and I believe of the two of these, I'm gonna do the top one, A, and I think I'm going to start by going ahead and just, I'm going to deal with this negative 6 here first. So I'm going to rewrite this equation, or this expression rather. In my numerator, I will have in parentheses 5a to the negative second, b to the third, and this is being raised to the 8th power. And then in my denominator, I'm going to go ahead and write 5a b to the negative second power. And because I've moved this down, right, this is now a positive 6. And we're very clear on the precise mathematical mechanics that allows us to do that. It's by multiplying by this giant 1, and we've done that many, many times during this school year. So in my numerator, I'm raising this whole base that's in parentheses to a power of 8. So I can accomplish that by raising each one of the individual pieces of this product to the 8th power. So this could be rewritten as 5 to the 8th power times a to the negative 16th power times b to the 3 times 8, which is 24th power. Very nice. In my denominator, I'm going to do the similar thing. I'm going to write this as 5 to the 6th power, a to the 6th power, and then b to the negative 12th power. Now you can see there's a couple places where I've got negative exponents, right? I've got a to the negative 16th, and I've got b to the negative 12th. And I can take care of both of those in one step, right? And I'll show that this process this time. If I multiply my numerator by, if I put in my numerator a to the positive 16th and the denominator a to the positive 16th, that's going to neutralize that a to the negative 16th, because a to the negative 16th times a to the 16th equals a to the 0, which is 0. Let me write that down. A to the negative 16th, that's in the numerator, times a to the positive 16th is a to the 0th power, which is equal to 1. So that's gone. And let's do a similar thing with this b, right? There's 12 factors of b to the negative 12th in my denominator. So I can multiply both the numerator and denominator by b to the positive 12th power, b to the positive 12th power. Now, when I do that, my expression simplifies, I think, considerably. I end up getting 5 to the 8th, and then times b to the, let's get this right, I'm adding 12 factors of b to that numerator, so it's going to be b to the 36th power, and then there's no a's up there. In my denominator, I'm going to have 5 to the 6th power times a to the, let's see, 16 and 6, which would be the 22nd power, a to the 22nd power, and I'm very close to being done. I just want to clean up these factors of 5. You can see my numerator has 8 factors of 5, and the denominator has 6 factors of 5. And if I was to write that out in expanded form and simplify it, I would see, oh, there's two factors of 5 left over. Of course, the shortcut is that's 5 to the 8 minus 6, which is equal to 5 to the 2nd power. Well, 5 to the 2nd power, that's the number 25. So here's the answer. I'm going to write down my final answer. I'm going to write 25 b to the 36th power over a to the 22nd power. Notice there are no negative exponents, and there's no giant ones left over, right? Everything has been simplified fully. So this would be our final answer. B, I'm leaving to you completely on your own. So that's the end of the homework help for the first section in Chapter 9. This is Mr. Roberts. Goodbye.